136.8 degrees Celsius. That is the gap between the hottest and coldest temperatures measured on Earth this year, a wider range than the entire gap between freezing and boiling water. And the two events that produced that number happened within days of each other, driven by the same piece of atmospheric machinery. By the end of this, you'll understand exactly what connects them. On July 18, 2026, a thermometer on the East Antarctic Plateau recorded minus 84.1 degrees Celsius, minus 119.4. Fahrenheit, at Concordia Station, a joint French-Italian research base sitting more than 10,000 feet above sea level on the interior ice sheet. It's the lowest air temperature measured anywhere on the planet's surface since 2012, and it came within roughly half a degree of Concordia's own all-time station record. Concordia is one of only 3 inland Antarctic stations occupied year-round, so there are people there right now, in the middle of a 4-month polar night, watching instruments produce a reading like this. It's worth being precise about what actually holds the recognized title here, because there's a confusing set of numbers in circulation. Satellite instruments have measured lower values on the East Antarctic Plateau, figures around minus 93 to minus 98 Celsius reported from orbit. Those are remote-sensed skin temperatures, the temperature of the snow surface itself, not standard air temperature readings, and they're not what the record books track. Concordia's minus 84.1 is a conventional air temperature taken at a staffed station, and that's the number that matters for this comparison. Just days earlier, and on the opposite side of the globe, Death Valley reached 121 degrees Fahrenheit, and Armstrong, Ontario hit 40.8 Celsius, its first 40-degree reading since 1995, and likely its warmest since the 1930s Dust Bowl. The single hottest temperature recorded anywhere on Earth so far this year came from Omidyar, Iran, at 52.7 Celsius, 126.9 Fahrenheit. Measured against Concordia's minus 84.1, that's the 136.8 degree spread, large enough to make Earth look like 2 different planets measured on the same day. There's also a specific claim circulating from Argentina worth handling carefully rather than repeating as settled fact. Charts built on Argentine National Weather Service data have circulated online, showing the city of Salta recording an overnight low that never fell below roughly 26 degrees Celsius on July 18th, which would be the warmest night in more than a century of that station's records, against a climatological normal for that date of around 3 degrees. That underlying data set is legitimate Argentine government data, but the specific hottest night in 101 years record claim has not yet been confirmed through an official agency bulletin as of this recording. So treat it as reported rather than certified. It's the kind of claim worth watching for an official correction or confirmation rather than either dismissing or repeating with full confidence. Here's why a record overnight low, if confirmed, would actually carry more weight than a record daytime high. Daytime highs are noisy. A break in cloud cover or a shift in wind can spike a single afternoon reading. Overnight minimums are different. Keeping a city from cooling off overnight requires the entire air mass above it to stay warm through its depth, plus enough humidity or cloud cover to stop the surface from radiating heat away after dark. A record warm night describes the state of the atmosphere over an entire region, not one hot afternoon at one thermometer. So why would the coldest reading on the planet in 14 years and reports of record subtropical warmth show up in the same window, on the same hemisphere, in the same season? The mechanism is a structure in the stratosphere over Antarctica called the polar vortex, a ring of fast westerly winds encircling the continent that isolates the air trapped beneath it from the rest of the planet. When that ring holds tight, the air underneath gets no sunlight because it's polar night, almost no water vapor because the air is thin, cold, and dry, and no mixing with warmer mid-latitude air because the wind ring won't let it through. The trapped air radiates heat to space and gets nothing back, and the temperature falls toward the coldest value the planet's surface can physically produce. That's exactly the setup that produced Concordia's reading. There's an index that measures how tight that ring is, called the Antarctic Oscillation, closely related to what's more commonly known as the Southern Annular Mode. Through the period surrounding this event, that index reportedly surged to strongly positive territory, a signature of a vortex that isn't merely present, but unusually tight, fast, and well organized. Ensemble modeling for the same period showed most of the Antarctic continent, not just one corner of it, running more than 20 degrees Celsius colder than normal, a continental-scale cold anomaly arriving at the same moment the Northern Hemisphere was moving through one of its most record-dense summers on record, with more than 100 countries reporting temperature records this year. The vortex doesn't just have a strength, it has a position, and that position matters downstream. When its core sits near and west of the Amundsen Sea, as it reportedly did this winter, that configuration historically induces a trough in the atmosphere off the central east coast of South America. That trough steers the wave pattern across the southern half of the continent, which is the physical link between a wind structure over Antarctica and the temperature pattern sitting over Argentina, Paraguay, and southern Brazil weeks later. To be clear about the mechanism, since it's easy to get this backwards, nobody is claiming cold air physically traveled from Antarctica to Argentina and somehow arrived warm. What travels is the shape of the atmosphere. A vortex anchored in one position bends the jet stream into a specific set of ridges and troughs downstream, and those ridges and troughs determine which air masses end up sitting over which countries. Shift the pattern by a few hundred kilometers, or flip it to the opposite phase, and the same country can go from importing polar air to importing air out of the warm continental interior instead. Now, the single most common misreading of this event needs to be addressed directly because it started circulating within hours of the Concordia figure appearing. The claim is that a record cold reading somehow disproves the broader warming trend. Here's the actual arithmetic. The coldest temperature ever reliably recorded on Earth is minus 89.2 Celsius at Vostok Station in Antarctica, set on July 21st, 1983. This year's reading, minus 84.1, is 5.1 degrees warmer than that 4-decade-old benchmark. A cold record that misses a 43-year-old mark by more than 5 degrees isn't evidence of a cooling planet, and coldest since 2012 is a 14-year statement about conditions at one station sitting in permanent winter darkness, not a global statement about anything. In the same year this reading occurred, more than 100 countries set heat records. The world's oceans had their hottest June ever measured. And a European heat wave in late June was associated with more than 10,000 excess deaths. There's one legitimate point buried inside that misreading, and it's worth conceding directly. Cold records genuinely do still occur in a warming world, and coverage that implies otherwise or that only reports one direction of extreme is an understandable source of public frustration and occasionally fair criticism of how these stories get covered. The conclusion some people draw from that frustration, that this disproves the broader trend, doesn't follow from the underlying physics, but the complaint about selective reporting has some real merit to it. Two quick related claims are worth closing off as well. The Concordia figure came directly from the monitoring network itself and was reported publicly within about a day. So this wasn't a suppressed or hidden reading, and there's no mechanism by which anything short of the full scale of tropical thunderstorm activity and planetary scale wave propagation, forces operating across thousands of kilometers of atmosphere, could produce or engineer an event like this. So the lid held this time, and the plateau got cold as a result. What happens when the lid doesn't hold has already happened once recently, and there's now a peer-reviewed paper on exactly what followed. In July and August of 2024, East Antarctica experienced what researchers describe as the most intense winter heat wave of the 46-year satellite era. Across a region called Drawning Maudland, average surface air temperatures ran more than 9 degrees Celsius above the climatological mean for 17 consecutive days, with peak anomalies at individual research stations reaching roughly 30 degrees above normal in the middle of the Antarctic winter. The estimated return period for an event of that scale was on the order of once every 135 years. The trigger, consistent with the same mechanism described above, was the earliest sudden stratospheric warming ever recorded in the Southern Hemisphere since satellite monitoring began in 1979, which left the vortex weakened and displaced after wave activity traced back to enhanced thunderstorm activity near Australia, and wave trains propagating poleward from South America and the subtropical Atlantic. That paper, published in NPJ Climate and Atmospheric Science, estimated that human-driven warming intensified the 2024 event by roughly 7 degrees Celsius, and more than doubled the likelihood of that class of event occurring in today's climate, compared with a world without that warming. The author's own framing is worth stating directly. What would have been a multi-century event under natural forcing alone has become a centennial-scale event today, with the likelihood of similar events projected to rise several-fold further under continued emissions by the end of the century. The authors are also careful to note real uncertainty in their own findings, including that they found no robust trend in how often the underlying circulation pattern itself occurs, and critically, that even during that record-breaking 2024 heat wave, most surface temperatures over the interior plateau remained well below the melting point. That last detail matters enormously because there's a second, less covered Antarctic temperature record from recent Southern Hemisphere winters that illustrates why. At Esperanza Base, on the northern tip of the Antarctic Peninsula, a winter temperature record around 4 degrees Celsius was observed, with nearby stations logging similarly extreme warmth and daily maximum temperatures in that region staying above freezing for nearly 3 straight weeks in the middle of winter. That produced real melting at glacier bases in the region, with bare ground appearing where ice normally sits, a physical change with its own feedback. Snow and ice reflect most incoming sunlight, while exposed rock and soil absorb it and radiate that heat into the surrounding ice. So once a patch opens, it tends to widen faster than temperature alone would suggest. That's the distinction that actually matters here, more than any single record on its own. A vortex breakdown over the dry interior plateau can produce a spectacular number on a chart, a 30-degree anomaly that takes you from roughly minus 60 to roughly minus 30 without melting anything at all. A vortex breakdown positioned over coastal ice, the ice that's actually in contact with the ocean, and that buttresses what sits behind it, produces something else entirely, because that's ice that can and does cross the melting point. So here's where this actually stands. Antarctica's overall regional warming trend runs at roughly half a degree per decade, and the likelihood of these vortex breakdown events has already roughly doubled due to human-driven warming, even though the frequency of the underlying circulation pattern itself shows no robust trend of its own. The swings themselves aren't obviously happening more often. The background they're swinging against has shifted, so when a swing does happen, in either direction, it now lands further from normal than it used to. On sea ice specifically, one honest caveat. Antarctic sea ice reached its annual minimum this year at a level ranking among the lowest in the roughly 5-decade satellite record. A partial recovery after several severe years, but still well below the long-term average, and the current growth season is again tracking low. That's a genuinely mixed picture. And any narrative of imminent total collapse built from a single year's numbers goes beyond what the data actually supports. And on the sun, since the question always comes up, solar activity around this period was moderate and declining, with quiet geomagnetic conditions on the days these records were set. There's no physical mechanism by which solar activity produces a strongly positive Antarctic oscillation on one side of the planet and a record warm night on the other on the same afternoon. What's worth actually tracking going forward is the Antarctic Oscillation Index itself, published continuously, since it's the clearest available signal for whether the vortex is tightening or breaking down at any given moment. Sudden stratospheric warming events in the Southern Hemisphere are historically rare, and the 2024 event arrived earlier in the season than any on record, which means timing itself has become part of the signal worth watching, not just magnitude. The real open question isn't which single record, the cold one or the warm one, matters more in isolation. It's what happens the first time a vortex breakdown of the 2024 scale parks itself directly over coastal ice rather than the dry interior plateau, and whether the difference would even be widely recognized while it was actually happening.